Hello, this is John Matsubara, and the atomic physics subject that I'm going to be discussing in this video is nuclear power. So first, let's talk about why it's important. Today we are too heavily dependent on fossil fuels for energy. Here in the US, around 81% of our energy comes from coal, natural gas, and oil. This is not good because fossil fuels are limited resources that we can run out of. The British Petroleum's 2019 statistical review of world energy predicted that we should run out of oil in 2067 at current consumption rates. Burning fossil fuels also releases CO2 or carbon dioxide, which contributes to climate change, threatening ecosystems and causing problems such as wildfires, tropical storms, and droughts. And it looks as though things are only getting worse, since carbon emissions have increased by 90% since 1970. And although renewable energy has seen some progress in recent years, we need more to meet growing energy demands. We need more renewable energy, and that's where nuclear power comes in. So what exactly is nuclear power? It's energy that comes from matter, which is then turned into electricity. Nuclear energy is considered renewable because so much of it can be produced from a small amount of matter, so it doesn't currently put us at a significant risk of running out of any natural resources at all. It is produced through nuclear fission, or the splitting of atoms, and this process happens inside nuclear reactors at nuclear power plants. So here's a brief history of nuclear reactors. Nuclear fission was first discovered in 1938 by physicists Lise Meitner and Robert Otto Fritzsche and chemists Otto Hahn and Fritz Strassmann. The first nuclear reactor creating electricity was created in 1951 in Idaho. In 1954, the first commercial nuclear power plant was created in the Soviet Union. Today, nuclear power plants account for about 10% of the world's energy production. Now let's talk about how nuclear reactors work. We first need to consider Einstein's equation E equals mc squared, meaning that energy is equivalent to mass times the speed of light squared. What this tells us is that a small amount of matter can be converted into a relatively enormous amount of energy. And this generally occurs when uranium undergoes the process of fission. This creates an intense source of heat, which is used for the generation of power. How this works is that the heat is used to turn water into steam, which turns the turbines of an electric generator, creating electricity. Nuclear reactors are enclosed in a shield of thick concrete wall. They have 5 main parts: a reactor core, a pump, a heat exchanger, a turbine, and a generator. The reactor core is where the fission happens, and the heat exchanger has water flowing through it. The pump connects these two so that the energy from the core heats up the water in the heat exchanger, creating steam. This steam turns the turbines, allowing the generator to produce electricity. There are 3 main components in the reactor core: the fuel elements, a moderator, and control rods. The fuel elements are thin rods about 1 centimeter in diameter, with fissionable nuclides like uranium-235 or uranium-238, and these rods are in the reactor core. Water is generally the moderator. Fuel rods are placed in the water to slow down neutrons produced by fuel elements in the fission process. Neutrons released from fission are given out with an energy of 1 megaelectron volt or 1 million electron volts, but these are slowed down when they collide with water molecules. And moderators also help create chain reactions in fission. Control rods are generally made of boron or cadmium, and these absorb excess neutrons inside the moderator to prevent further fission and keep the fission rate predictable. Rods can be removed or inserted to control the rate of fission reactions, maintaining a steady output of energy. In order to understand how nuclear reactors work, we first need to understand the process of fission. This is when unstable radioactive nuclei create strong radiations. Fission occurs when uranium-235 or uranium-238 emit radiation and turn into stable elements emitting 1 to 5 megaelectron volts. A uranium-235 nucleus bombarded with neutrons absorbs 1 neutron, becoming uranium-236, which is a highly unstable compound nucleus, and then this breaks into 2 equal parts, emitting a huge amount of energy. This is an example of an equation for this fission reaction. A neutron enters a uranium-235 nucleus, creating a compound nucleus, which is uranium-236. Uranium-236 is unstable, so it breaks down into barium-141 and krypton-92 and 3 neutrons. As you can see, the proton numbers of barium-141 and krypton-92 add up to the proton number of uranium-236, which is 92. However, the atomic mass numbers do not add up to 236, so 3 additional neutrons are needed to balance the equation. These excess neutrons can cause more atoms to go through the same process, creating a chain reaction. So, what are some benefits to nuclear energy? The first is that producing nuclear energy doesn't require much land compared to other forms of clean energy. For example, to produce 1,000 megawatts a day, which is enough to power around 164,000 homes, a nuclear power plant only needs to take up around a square mile of land. A solar plant would require around 75 times more land, and a wind farm would require as much as 360 times more land. Nuclear energy does not release carbon dioxide into the atmosphere like burning carbon fuels, so it has the potential to help slow global warming. In 2019, burning fossil fuels would have released around 476 million metric tons of carbon dioxide into the atmosphere to generate the same electricity nuclear energy did. In other words, in 2019, nuclear energy saved around 100 million cars worth of carbon emissions. Nuclear energy doesn't produce much waste compared to more conventional energy sources, and virtually all the waste is regulated and disposed of as safely as possible. That being said, we should also consider the drawbacks to nuclear energy. One of the most important is that it produces high-level nuclear waste, or HLW. If not contained correctly, this waste is extremely hazardous. Radioactive isotopes such as Tc-99, Se-79, and I-129 are mobile in water. If they contaminated groundwater, there could be deadly consequences. A perfect example of how dangerous nuclear energy can be was demonstrated at Chernobyl. In 1986, a poor design combined with human error led to an explosion at a reactor. This incident took the lives of over 50 firefighters, 3 workers, and is predicted to cause over 4,000 deaths related to cancer among civilians. 350,000 people had to be evacuated. In 2011, 4 reactors suffered meltdowns and explosions in Fukushima, Japan. This was due to a combination of factors including an earthquake of a 9.0 magnitude and a 15-meter tsunami striking at the same time. The tsunami disabled 12 out of 13 backup generators, and the cooling mechanisms of 3 reactors failed, causing meltdowns. 150,000 people had to be evacuated, but luckily no one died as a direct result of the meltdown. There is also the concern that commercial nuclear technologies could potentially be weaponized in the wrong places, such as Iran, for example. Nuclear proliferation, or the introduction of nuclear weapons technologies to new states, is a potential drawback to the spread of nuclear power. Terrorism might also be a concern for nuclear power, as nuclear power plants were seen as potential targets in the planning of the 9/11 attacks. Let's talk more about HLW, or high-level waste, in more detail. High-level waste consists of actinides, or radioactive elements that are the products of fission reactions. There are 2 types of high-level waste, and they are very distinct: spent or used reactor fuel, and the remnants of reprocessed fuel. Spent fuel is nuclear fuel in a reactor with a slowed rate of fission that is no longer producing electricity efficiently. Spent fuel is extremely radioactive, hot, and hazardous if not dealt with properly. The former type of HLW occurs when the spent fuel is disposed of. However, spent fuel can also be reprocessed when isotopes are extracted and reused as nuclear fuel. High-level waste is what's left after the reprocessing in this case. Reprocessing can reduce the volume of HLW by around 85%. Something important to note is that 95% of the radioactivity of the products of fission is in high-level waste. And this high-level waste only becomes harmless through decay, which can take hundreds of thousands of years. For all these reasons, high-level waste must be dealt with using extreme care. Now let's talk more about reprocessing. In reprocessing, plutonium is extracted from the spent fuel and then mixed with depleted uranium oxide to make new fuel. This allows for 25 to 30% more energy to be extracted from the original uranium. Reprocessing also drastically reduces the amount of time it takes for HLW to decay back into its original level of radioactivity before the uranium went through fission. The time can be decreased from around 300,000 years all the way down to just 9,000 years. One method used to address the drawbacks of nuclear power is nuclear vitrification. Nuclear vitrification is the safest known way to contain high-level waste. This immobilizes HLW by turning it into glass. So the process is as follows. First, the HLW is dried and heated, converting nitrates to oxides. Then glass-forming additives are added. It is then heated to around 1000 degrees Celsius or 1832 degrees Fahrenheit. The molten liquid is put into containers and allowed to cool until it forms borosilicate glass. These containers are then buried. The structure of the glass immobilizes the HLW. The glass is durable, providing long-term protection, and insoluble, preventing water contamination. Borosilicate glass remains stable for thousands of years, ensuring long-term protection. That being said, there are a few problems with vitrification. The first is that it's very expensive. It requires costly equipment, and it's a costly process. However, it is economically viable in places with enough high-level waste to create a demand for it. Another drawback is that borosilicate glass cannot contain much molybdenum trioxide. Now let's talk more about the future of nuclear power. Professor Barry W. Brook believes that nuclear energy has the potential to compete with or even oust fossil fuels completely in the next 10 years. The main hindrance to the advancement of nuclear power, in his opinion, is a lack of social acceptance and political fuel. Nuclear power is highly controversial because it comes with so many important benefits and unsettling risks at the same time. There are reasons to believe that nuclear power will become more prominent in the future because it doesn't have the same technical limitations as other power sources. It isn't nearly as limited in quantity as fossil fuels, such as oil, for example, which is projected to be used up around 2067. It also doesn't require as much land to generate electricity as solar or wind farms, as mentioned before. Nuclear energy is also much more reliable than solar and wind farms, which depend on the weather to produce electricity and can only be located in sunny or windy areas. A few countries have already eagerly adopted nuclear power. France, for example, currently gets 70% of its electricity from nuclear power. Now, looking at the data over the past few decades, it looks as though the growth of nuclear power in the world may have been stunted to some extent. While it rose steadily in the 1900s, it hit a peak in 2006 at 2,715 terawatts, declined for a few years, went up to 2,721 terawatts in 2019, and declined again in 2020. This shows that although nuclear power has the potential to grow in the future, the current rate of growth has been slowed significantly. Taking everything we've learned into consideration, we should weigh the risks of using nuclear power. Going into this project, I was very skeptical of nuclear energy because I knew that it can be extremely hazardous. But after learning more about the advantages of nuclear power over fossil fuels and other forms of renewable energy, I started to understand why it might be necessary. Learning about the process of vitrification eased my fear towards nuclear power a lot because I assumed people were simply dumping large amounts of hazardous nuclear waste into the ground. But it's reassuring to know that vitrification should theoretically keep the HLW immobilized for thousands of years. However, I still think nuclear power should be used with extreme caution considering how dangerous mishaps can be, like what happened at Chernobyl or Fukushima. And these are my sources.